Okay, so the change in potential energy is mg later height minus mg earlier height. So that is 10 times, we're using 9.7 as the acceleration of gravity. The elevation decreases 50 meters. So you can see that I could, associate these together, and this change is just going to be minus 50. So we have 500 times. Can someone tell me what negative 500 times 9.7 is?
Negative 4,850.
4,850 joules. Okay, we're getting there. And so now we also know a change in the specific internal energy. The actual internal energy is the mass. So that was a change. So the change in internal energy is the mass of the system times the change in specific internal energy. No. This is crazy.
It's just refined and over again. It takes you out every time.
Yeah.
That's.
So what was this, 5, and it decreases? And so we have a decrease of negative 50 joules there. And, okay, so now, and what do we know about, so heat goes out of the system. So the last thing we have to do, 5 kilojoules per kilogram. So we're going to have to, so heat is going to be plus or minus the mass times 5. So that's plus or minus 50 joules. And now we have to think, okay, heat is coming out of the system. Is that a positive or a negative Q?
Negative.
That's negative. And with that, always think about a power cycle. So a power cycle, heat goes into the system and work comes out of the system. So now we can finally write this whole thing. So we have the change in kinetic energy, 3375. That's okay, I like this. I like doing this.
It's Friday.
Yeah. 33. Okay. 3375. Yeah, long weekend too. Minus 4850. Minus 50. Oh no, I put that in the wrong place. Sorry. Where's my internal energy? Oh, they're both minus 50. Okay, minus 50. And then Q is minus 50 minus W. And now we're just solving for W. So what do you get there for W? 1,475. Is that what it is?
Yep. Yeah, I just have a hard
Joules.
reading it. There's so many things.
Yeah. I mean, yeah, you have. That's kind of a thing you're going to have to get used to in this class, just laying out a million things and just having faith that you're going to be able to work through it piece by piece. You know what I mean?
Yeah.
I mean, you always, you know what equation you're heading to almost always, you know? And if you can identify that, then you're just like, okay, I need this, I need this, I need this, and little by little, you know. But yeah, there are definitely some disciplines where you're like, right from the start, you know exactly where you're going. I find with this stuff, like you just kind of have to write out what you need and just go piece by piece. You won't see it all in an instant,
Yeah.
but just knowing where you're going, you know, you can get there.
I got tripped up when the velocity changed. I was like, that's not static equilibrium. And then I was like,
Oh yeah, exactly. I know. Wait till you go to dynamics and like all of a sudden you can't choose your about point. Okay, so any other homework questions? So last time we started talking about the differential form of the first law. And that said that dE dt is equal to Q dot minus W dot. And if you're in steady state, which a lot of problems say you are, then dE dt is 0. That's okay, I wanted that symbol there. Okay, and one of the things we're going to use this with is heat transfer. Close. It's going to close. I don't know where the, like where it's, I'll bet it's saving like backups and stuff to some internet drive, and that's why I'll bet it's like a Wi-Fi connection.
I wonder if IT would be an idea.
Yeah.
They're giving you a backup style, so you can have like one charging.
Yeah. I thought it was charging, but it doesn't seem to be, because it seems like if I just put it back in there for a second, it's like it remembers it or something. But anyways, okay, so we're here, and one of the big places we're going to use this is with heat transfer problems. Okay, so heat transfer, there are 3 modes of heat transfer. Those are conduction, radiation, and convection. And we're just going to go through convection. We're going to go through equations for each of these 3, and then we'll use it with the differential form of the first law. Okay, so first let's do conduction. The equation for conduction, okay, so let me define it first. So conduction is when energy is transferred through a material. So there has to be matter involved. Particle to particle. Without the particles changing location. So I mentioned the pan on the stove. You know, the fire is actually heating up the bottom of the pan, but eventually that energy will transfer to the handle.
So would like an incandescent light bulb heating up the air around it, is that not conduction, is that radiation?
It's a little of both.
Okay.
It's mostly radiation, though. Yeah. Okay, so the formula for conduction is Q dot is equal to negative Greek letter kappa times A times dt dx. This is a gradient, a temperature gradient. So all of these things are driven by a temperature difference. Okay, so Q dot is the heat transfer. Kappa is called the thermal conductivity of the material. So that's something you look up for the material. A is the cross-sectional area perpendicular to the energy flow. I'll draw a picture. So if conduction is happening this way, the cross-sectional area A that we want is this. T is the material temperature at a given X location. And X is the position along the path of the heat transfer. Okay, this equation always has a negative sign in it, but I'd recommend just forgetting about that and just doing the direction of heat transfer by intuition. I mean, you always know that heat is being transferred from the higher temperature to the lower. It never goes the other way. So forget about that. That sign convention, so remember, this is true for all of these. The sign that comes out of this conduction equation doesn't have a relationship to the sign convention that we use with the first law. So you have to think about, well, it isn't related to the first law sign convention. So just find the magnitude of Q dot. And then apply the first law sign convention. And by the first law sign convention, I mean thinking about a power cycle, you know, where you're heating up the system and heat is going into the system and work is coming out of the system. So, and then apply the first law sign convention. You understand what I'm saying with this? Okay, so let's do an example. So let's say we have a window. And let's say it's 1 meter by 1 meter. The thickness, we'll say, is 2 centimeters, so 0.02 meters. And it's a square where these dimensions are 1 meter. The thermal conductivity of the glass is 1.05 watts per meters Kelvin. And the temperatures on this side, we have 15 degrees Celsius. And on this side, we have 20 degrees Celsius on the back side. Okay, so first, if the temperature varies linearly through the glass, what's the heat transfer? The rate of heat transfer. So that's just going to be using the conduction equation. And then the second question is, okay, well, what's our system going to be? We're talking about heat transfer from one side of this glass to the other, you know? So our system is going to be one side of the glass. It's not going to be the glass itself. So let's say that if the system is the 20 degree side, what's the Q dot that we would use in the first law? Okay, so the first thing we're doing is just using this equation. So we're going to use the Q dot is equal to kappa times area times dt dx. And there's a negative, but we're going to ignore that. We already have kappa. What about A? What are we going to use for the cross-sectional area? So we have a few dimensions. Which area do we want?
1 meter by 1 meter.
That's right. Everybody see that? So it's the dimension that's perpendicular to the flow of the heat transfer. It's like, think of if the heat's moving through a window, it's the size of the window. That's actually what it is this time. So 1 meter times 1 meter, so 1 meter squared. Okay, now the gradient, dt dx. If we know that temperature varies linearly, then we can just think of this as a difference. Okay, so it's a total difference of 5 degrees Celsius divided by the distance over which that happens, which is 0.02. And so this is 250, right? And that would be Kelvin per meter. And so Q dot is equal to 1.05 times 1 times 250, and you get 262.5.
Oh, good for a while.
That was a good one. Yeah, that was a really good one. Okay, 262.5 joules per second, or watts. Okay. Any questions about that calculation? So I don't remember if every problem is going to be this way, but I mean, for the most part, you're not going to tend to know the function of temperature as it varies with x. And so you're just going to assume that there's a linear gradient. And so you're just going to do this as, using this difference equation. So, I did this as the change in temperature over the change in x. Okay. Now, so this was part A. Now for part B, we're going to assume that the system we care about is on the back side of that window. So is energy going to be leaving our system through heat or entering our system through heat? Leaving. It's always going from high to low. Okay? And so now think about the sign convention for the first law. Is that Q dot going to be positive or negative if it's leaving our system? Exactly. So, so energy through heat is leaving the system. So Q dot is equal to negative 262.5 joules per second. And now you have something that you can use in the first law if it's asking you to calculate the work or something. Any questions about that one? That one's conduction. So now we're going on to radiation. So any object above a temperature of absolute 0 emits radiation. And this radiation is electromagnetic waves. These waves can travel through empty space. That's the only one of these heat transfer mechanisms that doesn't require any molecules in the path. And, if that wasn't the case, we wouldn't have, there'd be no life, because that's how we get the energy from the sun. So radiation does not require a medium to transfer. does not require a medium to travel through.
There's no medium, is there no loss?
Yeah, I mean, it's, yeah, right. I guess as radiation travels through a material, like those little molecules are getting a little bit of that radiation. Yep. Yeah, that's right. Yep. So it's radiation is emitted from a material. So it's emitted according to the Stefan-Boltzmann law. And that says that Q dot sub E, the E is for emitted, so you remember which direction this is going, is equal to the Greek letter epsilon times the Greek letter sigma times A times temperature to the fourth. And this epsilon is called the emissivity. It's a pure number between 0 and 1. A matte black has an emissivity of 1, so it's very good at emitting radiation. Shiny white has an emissivity of 0. The Stefan-Boltzmann constant is the Greek letter sigma. And that is 5.67 times 10 to the minus 8 watts per meter squared Kelvin to the fourth. A is the surface area of the material. And T is the absolute. So we're going to use Kelvin for our absolute temperature. You could use Rankine too. The absolute temperature of the material. This one isn't very useful to us because this only tells you half of what you need to know for the first law about heat transfer, because heat is also being transferred into bodies from its surroundings, you know. So just knowing what heat is emitted doesn't really help you. You also need to know how much is being absorbed. But there is one case that we can deal with. So in general, we don't know the rate of absorption. But for a smaller body, completely surrounded by a larger body, The net heat emitted, and that's the one that we want for the equation for the first law, is the rate of heat emitted is equal to the emissivity times the Stefan-Boltzmann constant times the area of the smaller body, the surface area of the smaller body, times the quantity temperature of the body to the fourth power minus the temperature of the surroundings to the fourth power. Okay, so this A is the surface area of the smaller body. T sub B is the temperature of the smaller body. That's B for body. T sub S is the temperature of the surroundings. I mentioned before that in thinking about temperatures, you can think differently about differences in temperature than you do about absolute temperatures. Actual instantaneous temperatures. This is not a difference between temperatures. If this was not to the fourth power, if this was just to the first power, then we could do this in Celsius or whatever. But because of the fourth power, these have to be in Kelvin or Rankine, okay? So these have to be absolute. Okay, convection. Let's get this done. So convection is heat carried to a new location by moving particles. So that's like wind chill, water carrying heat away from your body. So heat carried to a new location by moving particles. The formula for this, Q dot is equal to H times A times T sub B minus T sub F. And the meanings of these things, H is just kind of a catch-all term. It's an experimental term for your specific case. So it includes a lot of stuff. But this has to be found experimentally. So you can think of the this expression for convection as being the least like a physics law. This one is just kind of like a curve fit for your specific case. A is the surface area of the body that's exposed to the fluid flow. T sub B is the temperature of the body. T sub F is the temperature of the fluid. And these temperatures, because this is a difference, this can be any type of temperature. Because, you know, the difference in Celsius temperature is the same as the difference in Kelvin temperature. Okay, so the main thing to notice, I guess I mentioned this before when we were talking about conduction, but you can't trust any of these signs for the first law of thermodynamics. You have to come up with your answer, and then from there evaluate whether heat is entering or leaving your system. Okay. So find your Q dot magnitude. And then think, is energy entering or leaving the system? Any questions about that? Okay, well, the next thing that I was going to do was 2 example problems. I think I don't have time to do that. If you want to see these example problems, you can look in the old notes from last year. I think on Wednesday I'll probably go through 1 or 2 of these. So if you want to wait to work on the homework until Wednesday, you could do that. But really the basic approach to these kind of problems is you're going to use the heat transfer equations to come up with the magnitude of the rate of heat transfer. And then you're going to put that into the first law with the appropriate sign convention and calculate other stuff. You know, maybe you'll calculate the internal energy, or maybe you'll calculate the rate of work done or whatever, but that's sort of the approach. Okay, that's all.